Hello everybody, okay, and we're back, and this video is all about continuity, okay? Continuity, I believe, is discussed in section 1.11. I have to admit, I'm not sure why it's discussed so late in the chapter, but, you know, oh well. Continuity, so we have already learned that for a limit to exist, that the limit as x approaches any x value from the left has to be identical to the limit as x approaches a from the right, and L has to be a real number. Okay? And if this happens, then we say the limit as x approaches a of f of x exists and equals L, whatever that number is. Okay? Now, continuity is what happens when you don't have to lift your pencil when sketching for any reason. Okay, so let's talk about this continuity over an interval. Let's say the interval is AB, like this. Okay, so what this means is basically from A to B, right? All x values from A to B when sketching F your utensil never leaves the graph or the paper. Okay. That is to say, you never have to lift your pencil or pen. Okay, never have to lift your pen or pencil from x equal a to x equal b. Okay, so what does that look like? I'm going to draw a bunch of examples of continuous curves. Okay, it could be negative. Let's say this is x equal a. Let's say this is x equal b. Okay, so here's a continuous curve. Let me change my color. I want to draw a continuous curve now. Here we go. There's a continuous curve. All right. Here's another continuous curve. There we go. That's continuous. Here's another continuous curve. All right. Let's see, what else? There's some curves that look like this. Okay. All of these are completely continuous. Okay. Continuous curves. All right. Now, over here on the right, I'm going to draw examples of curves that are discontinuous. Okay? All right. So, discontinuous curves. Discontinuous curves, okay? So let's still say we have A here and B all the way over here, just like before. Now, here's a sort of a subtle discontinuity. It's called a hole. It's called a hole. It's also called a removable discontinuity. Okay, so from the top example, this discontinuity that we see here in the middle, this is a hole. Also called a removable discontinuity. Removable discontinuity. And the reason that we call it removable is because we can just come and define a new function which is the same curve from before, in addition to this red point here. That is to say, let's suppose the blue curve here is f. Then what we can do is we can remove this hole by saying, okay, well, hey, let's define a new function called g, and let's let g be, ooh, you know what, that looks so bad, I'm gonna make a new one. Much better, okay. Let's let g be f of x, and I don't want to be, I want to be kind of general here. Let's say this is x equals c, okay? And the y value here, the y value of that hole, I don't know, let's call it, let's just for the sake of this video, let's just say it's 5, okay? We can define a new function g, which is exactly the same as f, which is the blue curve. And then we can throw this in. We can say, okay, well, you know what? At x equals c, this function is going to be 5. And that'll fill in. So now g is continuous now. We removed the hole. We removed the discontinuity there, okay? And the domain on f is going to be, it's going to be this, right? It's going to be all x between a and b, such that x is not c. Okay. So this is the domain for the f portion. So basically, this is the blue curve. This is the red dot. And if we combine the two, then we get something that we no longer have to remove our utensil. If I sketch across here in yellow, and I include the red point. If I include the red point, then check it out. I don't have to lift my pen. I can go straight through from A to B. Okay, so not the best trace there, but you get the idea. Okay, so that's what we'll call that a removable discontinuity. Any hole can be removed in the way that we have here. Okay. Let's talk about some other discontinuities. Let's see, one that we encountered in a couple of previous videos is something like this. Let's say we start here, and then let's say we have a hole here, and then let's say we come up here like this. Okay, so this little gap here, this little gap is called a jump discontinuity. Okay, and a jump discontinuity is just what I'm going to say, a finite vertical hop. Finite vertical hop up or down in the curve, or in the function. Okay, so that's a jump discontinuity. We encountered a function in a couple of videos ago. We used we were talking about the absolute value of x over x. This function has a discontinuity in it. Okay, a jump discontinuity to be specific. Okay. Good. Jump discontinuities in general are not removable. Okay. You know, even if we fill this hole in somehow, we still have this gap here. All right. I'm just going to make a new set of axes. Okay. So we got the removable discontinuity, we got the jump discontinuity. And then we also have infinite discontinuities, which we've talked about a little bit. So here's the infinite discontinuity. Anytime the function goes to plus or minus infinity, anytime there's a vertical asymptote, okay, then you have an infinite discontinuity. Okay, so here is a bunch of them shown here, right? So here is an infinite discontinuity right here. I'll just abbreviate it with disc. Here's one, and here's one. Okay, so we got four, right? 4 places, and then it looks like it goes up to infinity here as well. So anytime we have something like this where the function goes to plus or minus infinity, we call that infinite discontinuity. And you know, that's that. Let me make sure I haven't missed anything here. Okay. Yeah, I don't think so. Okay. So good. So, yeah, just to sort of summarize, right? A continuous function means that you can sketch from A to B without lifting your utensil at all. Okay, and then if you have to lift your utensil for any reason, we call that a discontinuity. Okay. Holes are removable. You can always fill in a hole. A jump discontinuity is a finite vertical hop, up or down. And then we have infinite discontinuities. Okay, anytime the function goes to plus or minus infinity, anytime there's a vertical asymptote, we have an infinite discontinuity, and of course these are not removable as well. Okay. Yeah, I think that's what I'll sum this video up. Just a little bit of background on some vocabulary and a continuous function versus a function that has discontinuities. Okay,